So everything you have ever seen is following rules. The coffee cooling on a desk, the light coming through the window, the weight of your own body pressing down into a chair, your phone that somehow knows where it is on the planet. None of it is making choices. All of it is obeying a small set of rules that were here long before anyone wrote them down. And the strange thing is that for almost all of human history, nobody knew what those rules were. We just lived inside them, the way a fish lives inside water without ever once thinking about the water. This is the story of how we figured them out. Not the rules themselves, exactly, but the long, slow, often embarrassing process of a species slowly waking up inside its own universe and starting to ask why things fall, why the sky is the color it is, why heat moves the way it does, and what light actually is. It is the history of physics, which is really just the history of people refusing to accept that the world is too complicated to understand. And the reason this is worth your time is that physics did not arrive all at once, handed down complete. It came in pieces, often by accident, frequently from people who were wrong about almost everything else. And the order in which it arrived tells you something about how hard it really is to see what is right in front of you. So, to understand where we are now, with our talk of black holes and quantum fields and an expanding universe, we have to go back to a time when the most advanced idea anyone had was that the world was made of water. To be clear about what we are doing here, physics is the study of the most basic stuff there is, not plants or animals or rocks specifically, but the things underneath all of those: matter, energy, motion, force, space, and time. Everything else, every other science, sits on top of physics the way a house sits on top of a foundation. And for most of the story you are about to hear, nobody even knew the foundation was down there. So let us start at the beginning, or at least the beginning of the part we can actually trace. The first people we know of who tried to explain the world without simply saying that the gods did it lived on the coast of what is now Turkey about 2,600 years ago, in a Greek trading city called Miletus. There was a man named Thales who looked at the world and decided that underneath all the different things he could see, there had to be one basic substance that everything was made of, and he guessed that this substance was water. Now, that is wrong. But the idea behind it, that the messy variety of the world might come down to something simpler underneath, is one of the most powerful ideas anyone has ever had, and it is still the idea driving physics today. We are still looking for the water. We just call it different things now. The Greeks who came after Thales kept playing this game. One of them, a man named Democritus, came up with an idea that should make the hair on your arms stand up a little when you realize how early it was. He suggested that if you took any object and cut it in half, and then cut that half in half, and kept going, you would eventually reach a piece so small that it could not be cut anymore. He called this smallest possible piece the atom, which in Greek just means uncuttable. He had no microscope, no experiment, no evidence of any kind. He simply reasoned his way to the idea that matter is made of tiny, indivisible bits, and he turned out to be roughly right about 2,300 years before anyone could prove it. He also turned out to be wrong about the uncuttable part, because we did eventually cut the atom, but we will get to that, and when we do, you should remember this moment. The trouble is that the Greek who became most influential was not Democritus, and he was not really doing physics the way we would recognize it. His name was Aristotle, and he was one of the great minds of the ancient world. But his approach to the physical world held science back for nearly 2,000 years, and it is worth understanding why. Because the way he got it wrong is so reasonable that you would probably have made the same mistake. Aristotle believed that heavier objects fall faster than lighter ones. And honestly, why wouldn't you believe that? Drop a stone and a feather at the same time, and the stone hits the ground first. It looks obvious. It looks like the most settled fact in the world. Aristotle also believed that objects only move when something pushes them, and that they naturally come to rest when the pushing stops. Which, again, look around. That is exactly what seems to happen. Push a cart and it rolls. Stop pushing and it stops. His physics was built on careful observation of the everyday world, and that was its great strength and its fatal weakness. Because the everyday world is full of complications like air resistance and friction that hide the simpler rules underneath. Aristotle was describing the surface of things beautifully while completely missing what was going on beneath. And because he was so respected, his answers were treated as final for almost 20 centuries. Nobody bothered to actually test them, which tells you something a little uncomfortable about how knowledge works, because a confident enough answer can stop people from looking for a better one. While Europe largely sat with Aristotle, some of the most important work kept the lights on elsewhere. During the centuries we sometimes lazily call the Dark Ages, scholars across the Islamic world were not only preserving the Greek texts, but pushing past them. The one who matters most for our story lived around 1,000 years ago and is usually known in the West as Al-Hazin, though his full name was Ibn al-Haytham. He worked in Cairo, and he did something genuinely new. He studied light and vision, and instead of just reasoning about it the way the Greeks would, he ran careful experiments. He built dark rooms with tiny holes to study how light traveled, and he insisted that ideas had to be tested against what you could actually observe. A lot of people consider him one of the first people to really use the scientific method, the basic loop of guess, test, and check. And that loop is the engine that drives everything that comes next. Without that loop, physics is just opinions. With it, physics becomes a way of forcing the universe to answer questions. But the real turning point, the moment the modern story properly begins, comes in Europe in the 1500s. And oddly enough, it starts not with physics, but with astronomy, with a quiet church official in Poland named Nicolaus Copernicus. For more than 1,000 years, everyone had agreed that the Earth sat still in the center of the universe, while the sun, the moon, and the stars all wheeled around it. This was not stupid. It is exactly what it looks like. You do not feel the earth moving, and the sun very clearly rises on one side of the sky and sets on the other. But there was a problem, and the problem was the planets. The word planet comes from a Greek word meaning wanderer, because the planets do not move smoothly across the sky like the stars. Every so often, a planet like Mars appears to stop, drift backward for a while, then turn around and continue forward, a strange little loop in the sky. To explain this while keeping the Earth in the center, astronomers had built an incredibly complicated system of circles riding on top of other circles, and it sort of worked, but it was a mess. Copernicus realized that if you simply put the sun in the center and let the Earth be just another planet moving around it, the strange, backward loops of the other planets fell out naturally as a side effect of us passing them or them passing us, the way a slower car next to you on the road seems to drift backward when you overtake it. He had taken a tangled problem and made it simple, and that simplicity was a clue that he was onto something true. He waited until he was dying to publish it in the year 1543, possibly because he knew how much trouble it would cause, and he was right to worry. The man who turned that idea into a weapon was an Italian named Galileo Galilei, and he is where physics really starts to look like physics. Galileo did two things that changed everything. The first is that he pointed a telescope at the sky, which had only just been invented, and he saw things that simply did not fit the old picture of a perfect, unchanging heavens that circled a central Earth. He saw mountains and craters on the moon, which meant the moon was a rough, rocky world like ours and not a perfect heavenly sphere. He saw that Jupiter had 4 little moons of its own going around it, which meant that not everything in the universe went around the Earth. He saw that Venus went through phases like our moon, growing and shrinking in a pattern that only made sense if it was orbiting the sun and not us. The evidence was right there in the eyepiece for anyone willing to look, and a lot of people famously refused to look because they already knew what the answer was supposed to be. But the second thing Galileo did matters even more for physics, and it is the thing that makes him the first real physicist. He went after Aristotle directly on the question of falling objects, and he did it by actually testing the claim instead of just believing it. There is a famous story that he dropped 2 balls of different weights from the Leaning Tower of Pisa to show they hit the ground at the same time, and historians are not sure that particular event really happened. So we should be honest about that. But what he definitely did was clever in a different way. He could not slow down a falling object to study it closely, so instead he rolled balls down gentle ramps, which is just falling slowed down, and he timed them carefully. And what he found was that the weight of the ball did not change how fast it sped up as it rolled. A heavy ball and a light ball gained speed at exactly the same rate. Aristotle had been wrong for 2,000 years, and the reason nobody had noticed was that in the real world, a feather really does fall slower than a stone, but only because the air gets in the way. Take the air away, and the feather and the stone fall together. Centuries later, astronauts standing on the moon, where there is no air at all, dropped a hammer and a feather side by side, and the whole world watched them hit the ground at the same instant. Galileo never got to see that, but he had figured it out from a ramp and a sense that the universe ought to be simpler than it looks. Galileo also worked out something even less obvious, the idea of inertia, which is the notion that an object in motion will just keep moving in a straight line forever unless something stops it. This sounds wrong, because nothing on earth seems to do that. But that is only because there is always something stopping things: friction from the ground, resistance from the air. Galileo realized that the natural state of a moving object is to keep moving, not to come to rest, and this completely flips Aristotle's picture on its head. For Galileo, you do not need a reason for something to keep moving. You need a reason for it to stop. While Galileo was looking through his telescope in Italy, there was another man off in Central Europe doing something just as important, with nothing but numbers and an almost superhuman patience. And the history books outside of science do not give him nearly enough credit. His name was Johannes Kepler, and he is the one who finally figured out the actual shape of the heavens. Kepler had inherited a treasure, which was the life's work of a Danish nobleman astronomer named Tycho Brahe, a colorful character who had lost part of his nose in a duel and wore a metal replacement, and who had spent decades making the most precise measurements of the positions of the planets that anyone had ever made, all by naked eye, because this was still just before the telescope. Tycho had the data but could not make sense of it, and when he died, Kepler got hold of those priceless records and spent years wrestling with them, especially with the stubborn motion of Mars, which simply refused to fit any circle he tried. And this matters because everyone, including Copernicus, had assumed that the planets must move in perfect circles, since the circle was considered the most perfect shape and the heavens were supposed to be perfect. Kepler tried for years to force Mars onto a circle, and the data kept missing by a tiny amount, an amount so small that a less honest man might have shrugged it off as measurement error. But Tycho's measurements were too good to ignore, and Kepler trusted them more than he trusted the ancient assumption, so he finally gave up the circle and tried a slightly squashed shape instead, an ellipse, a sort of stretched oval, and suddenly everything fit perfectly. The planets do not move in circles. They move in ellipses, with the sun sitting not at the center but off to one side, at a special point of the ellipse. This was Kepler's first law, and it broke a belief that had stood for 2,000 years. He found two more laws as well, precise mathematical rules describing how a planet speeds up when it swings closer to the sun and slows down when it drifts farther away, and exactly how a planet's distance from the sun relates to how long its year is. These three laws of Kepler's described for the very first time exactly how the planets actually move, not just roughly, but precisely, and he found them purely by staring at numbers until they confessed. He had no idea why the planets obeyed these rules, what force was behind them. That answer would have to wait for the man with the apple, who, when he came, would show that all three of Kepler's hard won laws fall straight out of a single equation for gravity, which is one of the great moments of two pieces of science clicking together. For pushing these ideas, and especially for arguing that the Earth really moves around the Sun, Galileo was put on trial by the Catholic Church in the year 1633, forced to take back what he had said, and kept under house arrest for the rest of his life. He is supposed to have muttered after recanting the phrase, "And yet it moves," referring to the Earth, though there is no good evidence he actually said it. He died still under house arrest in the year 1642. And here is one of those quiet coincidences that history hands you for free. Because in that same year, at least by the old calendar then used in England, off in England, a baby was born who would take everything Galileo had started and finish it so completely that the resulting picture of the universe would stand essentially unchallenged for the next 200 years. His name was Isaac Newton. It is hard to overstate what Newton did, so let me try to be specific rather than just calling him a genius and moving on. Before Newton, the heavens and the earth were thought to follow different rules. The motion of planets was one kind of thing, and the falling of an apple was another kind of thing entirely, and there was no reason to think they had anything to do with each other. Newton's enormous, world-changing idea was that they are the same thing. The force that pulls an apple to the ground is the exact same force that holds the moon in its path around the earth, and the earth in its path around the Sunday. He called it gravity, and he claimed that it was universal, that every single object in the universe with any mass at all pulls on every other object all the time, everywhere. The apple pulls on the earth just as the earth pulls on the apple, though because the earth is so much larger, you only notice one side of it. He went further than just naming it. He wrote down an exact equation for how strong this pull is, and the equation is beautiful in how simple it turned out to be. The force of gravity between two objects depends on how much mass each one has, and on how far apart they are. And specifically, it gets weaker with the square of the distance, which means that if you move twice as far away, the pull becomes not half as strong, but a quarter as strong, and at 3 times the distance, a ninth as strong. That one rule, written down in the 1680s, correctly describes the falling of an apple, the arc of a cannonball, the orbit of the moon, the paths of all the planets, the timing of the tides, and the return of comets, all of it with a single equation. He published all of this in the year 1687 in a book whose Latin title is usually shortened to the Principia, and it is one of the most important books ever written by anyone about anything. The astronomer Edmond Halley, the one the comet is named after, was so convinced of its importance that he paid for the printing out of his own pocket. Newton did not stop at gravity. He also laid down 3 rules for how all motion works, which we still call Newton's laws, and they are worth knowing because they run your entire physical life without your ever noticing. The first law is Galileo's inertia made official, that an object will keep doing whatever it is doing, sitting still or moving in a straight line until a force acts on it. The second law connects force, mass, and acceleration, and it says, in plain terms, that the heavier something is, the harder you have to push to change its motion, which is why a shopping cart is easy to get moving and a car is not. The third law is the famous one that for every action there is an equal and opposite reaction, which means that whenever you push on something, it pushes back on you with exactly the same force. This is not a metaphor. It is literally how a rocket works, by throwing gas downward, so the gas throws the rocket upward. And it is how you walk, by pushing backward on the ground, so the ground pushes you forward. And as if all that were not enough, Newton also invented an entirely new kind of mathematics, calculus, to handle the constant change involved in motion, doing it at roughly the same time as a German named Gottfried Leibniz, which led to one of the ugliest priority fights in the history of science. He also broke sunlight apart with a glass prism and showed that white light is secretly all the colors mixed together, which is the answer to the rainbow your younger self probably wondered about. When the dust settled, Newton had handed humanity something that looked very much like the complete instruction manual for the universe. You give me where everything is and how fast it is moving, the picture said, and I will tell you exactly where it will be at any moment in the future, forever. The universe looked like an enormous clockwork machine, perfectly predictable, ticking along according to fixed laws. This view was so powerful and so successful that physicists spent the next century just working out its consequences, and they got very good at it. During the 1700s, a handful of brilliant mathematicians took Newton's ideas and rebuilt them into forms that were even more powerful, even if they were less famous outside of physics. A Swiss mathematician named Leonhard Euler, who was so productive that he kept publishing for years after going completely blind, reworked the laws of motion into cleaner mathematical language. A French Italian named Joseph Louis Lagrange found a way to describe motion not by tracking forces and pushes directly, but by looking at energy, at a kind of balance between the energy of motion and the energy of position. And his approach turned out to be so deep that physicists still use it today to describe everything from a swinging pendulum to the behavior of particles. And the French scientist Pierre-Simon Laplace took the clockwork idea to its logical extreme. He argued that if some vast intelligence knew the position and motion of every single particle in the universe at one moment, it could calculate the entire future and the entire past with perfect certainty, because everything was just following Newton's laws. There was no room left for chance. The universe, in this view, was a film that had already been shot, and we were simply watching it play. Hold on to that idea, because the universe is going to take it away from us later in the most dramatic way possible. But while all this was happening, there was a whole side of nature that Newton's laws did not really touch, and it was something everyone experienced every single day. Heat. What is heat actually? Hold a cup of hot tea and you can feel it. But what is the thing you are feeling? For a long time, the leading idea was that heat was a kind of invisible, weightless fluid, which they called caloric, that flowed out of hot things and into cold things, and that you could not create or destroy. It is a perfectly reasonable guess, and it explained a lot. Hot things cool down because the caloric drains out of them into their cooler surroundings. The trouble came from a soldier and scientist named Benjamin Thompson, who, while supervising the boring of cannon barrels, noticed something odd. As the drill ground against the metal, it produced heat without end as long as the drilling continued. If heat were a fluid stored inside the metal, it should eventually run out, the way water runs out of a sponge. But it never ran out. The heat seemed to be created fresh by the motion of the drill, which suggested that heat was not a substance at all, but a form of motion, the invisible jiggling of the tiny pieces that make up the metal. He was right, though it took a long time for that to win out. This was the start of a part of physics called thermodynamics, which is the study of heat and energy and how they move around, and it produced some of the deepest and strangest laws in all of science. It began, of all places, with people trying to build better steam engines. A young French engineer named Sadi Carnot in the early 1800s asked a simple practical question, which was how efficient a steam engine could possibly be. And in answering it, he stumbled onto something far bigger than engines. He realized that there is a hard limit, set by the laws of nature themselves, on how much of the heat you put in can be turned into useful work, and that you can never reach 100%. No matter how cleverly you build your machine, some of the energy always escapes as waste heat. This is not a problem of engineering that better technology will someday solve. It is a rule of the universe. Out of this came one of the most profound ideas in physics, the second law of thermodynamics. And it is worth slowing down for because it touches everything, including you. The first law, which came together in the middle of the 1800s, thanks to people like James Joule, who carefully measured how mechanical motion turns into heat, says that energy can never be created or destroyed, only changed from one form to another. The energy in the gasoline becomes the motion of your car, becomes the heat in the brakes, but the total amount never changes. That law is a kind of cosmic accounting, and the books always balance. The second law is stranger. It says that heat always flows on its own from hot things to cold things, and never the other way, and more broadly, that things left to themselves always become more disordered, never more ordered. A hot coffee always cools to room temperature, and a cold coffee never spontaneously heats up by pulling warmth out of the room, even though the energy accounting would allow it either way. There is a direction to things. Physicists gave this tendency toward disorder a name, entropy, and the German physicist Rudolf Clausius stated the second law in a famous, almost ominous form, that the entropy of the universe as a whole always increases. A man named Ludwig Boltzmann then dug down and figured out what entropy really is at the level of atoms, and his answer is genuinely beautiful. Disorder wins simply because there are vastly more ways to be messy than to be tidy. Think of a deck of cards. There is only one arrangement that counts as perfectly sorted, but there are an astronomical number of arrangements that count as shuffled. So if you shuffle a sorted deck, of course it becomes disordered because almost every possible outcome is a disordered one. Heat spreads out and order falls apart for the same reason, because spread out and disordered is simply what most of the possibilities look like. Boltzmann turned the flow of time into a counting problem, and the equation that captures it is carved on his gravestone. The deeper idea underneath all of this was that heat and temperature are not substances at all, but simply motion, the ceaseless jiggling and bouncing of countless tiny atoms and molecules. Maxwell, the same Maxwell we will meet again with light, worked out the mathematics of how the atoms in a gas must be flying around at a huge range of speeds, some slow, some fast, with a definite spread of speeds that we now call the Maxwell-Boltzmann distribution. And from this picture, you can derive the everyday behavior of gases, why they press out on their containers, why they warm up when squeezed, why a smell spreads across a room. Temperature, in this view, is nothing more than the average energy of motion of those particles. When you heat your tea, you are literally making its molecules move faster. And when something cools, its molecules slow down. This leads to a natural question with a strange answer, which is, what happens if you keep cooling something down, slowing the motion more and more? There turns out to be a coldest possible temperature, a point where the motion is as still as the laws of nature allow, and it is called absolute zero, which is about negative 460 degrees on the Fahrenheit scale, and it can be approached ever more closely, but by another deep law, never quite reached. It is worth pausing to appreciate how controversial this all was at the time, because we take atoms completely for granted now, and it is easy to forget that as recently as a little over a century ago, many serious scientists flatly did not believe in them. To them, atoms were an unproven, possibly imaginary bookkeeping device, since no one had ever seen one, and an influential group led by a physicist and philosopher named Ernst Mach insisted that science should only talk about things you could directly observe. Boltzmann had built his entire account of heat and entropy on the reality of atoms, and he spent the last part of his life defending that idea against fierce opposition from people who thought he was chasing a fiction. The cruel irony is that the proof arrived almost the moment he was gone, because Einstein's 1905 paper on the jittery dance of pollen grains in water, that random twitching that could only be explained by countless invisible water molecules knocking the grains around, gave the exact testable prediction that careful experiments would soon confirm, finally proving that atoms are real. The debate Boltzmann had agonized over was settled in his favor right around the time of his death. And here is where two true facts sit side by side in a way that should give you pause. The same process that cools your coffee, the relentless spreading out of energy and the steady increase of disorder, is, as far as we can tell, the reason that time has a direction at all. The laws of motion that Newton wrote down work exactly the same whether you run them forward or backward, like a film that makes sense played either way. But the second law does not. It only runs one way. And so, the reason you remember the past and not the future, the reason a broken glass never reassembles itself, the reason you are getting older and not younger, may all come down to the simple fact that there are more ways to be messy than to be neat. Boltzmann himself struggled terribly in his life and died by his own hand before the atomic picture he had fought for was fully accepted, which is one of the sadder turns in this story. I will note, since the topic has come up, that if any of this brushes against something heavy for you, it is worth reaching out to someone you trust. So, by the middle of the 1800s, physics had two great pillars. It had Newton's mechanics, which handled motion and gravity and the clockwork of the heavens, and it had thermodynamics, which handled heat and energy and the strange one-way flow of time. But there was a third great mystery that neither of these touched, and it had been sitting in plain sight since the ancient world in the form of two odd phenomena that seemed completely unrelated to each other. Electricity, the spark and the shock, and magnetism, the strange pull of a lodestone. People had known about both for thousands of years without having any idea what they were. The ancient Greeks knew that if you rubbed a piece of amber with fur, it would attract little bits of straw, and the Greek word for amber is where we get the word electricity. They also knew that certain rocks, lodestones, would pull on iron all by themselves, and that a sliver of such a rock, floated on water, would swing around to point north, which is how the compass was born. But electricity and magnetism seem to be two completely separate curiosities, two unrelated party tricks of nature, and nobody had any reason to think they were connected. The story of the 1800s in physics is largely the story of discovering that they are not just connected, they are two faces of the same thing, and that this single thing also turns out to be light. It is one of the great unifications in the history of science, and it happened in a chain of discoveries that built on each other almost perfectly. It started to come together when an Italian named Alessandro Volta invented the first real battery around the year 1800, a stack of metal discs and salty cardboard that, for the first time, gave scientists a steady, controllable flow of electricity to experiment with, instead of just sparks and shocks. Suddenly, you could run a current through a wire and watch what it did, and what it did turned out to be astonishing. In the year 1820, a Danish scientist named Hans Christian Ørsted was giving a lecture when he noticed that a compass needle sitting near a wire twitched whenever he switched the current on and off. The electricity in the wire was pushing on the magnet. This was the first hard proof that electricity and magnetism were talking to each other, and it caused a sensation because it meant the two great mysteries were somehow one mystery. A current of electricity creates a magnetic force around it. Other scientists pounced on this. A Frenchman named André Marie Ampère quickly worked out the mathematics of how currents and magnets push on each other, which is why the unit we measure electric current in is now called the amp after him. But the real hero of this part of the story is a man who started with almost nothing, an Englishman named Michael Faraday, who came from a poor family, had little formal schooling, and began his career as a bookbinder's assistant before talking his way into a job working as a laboratory assistant at the Royal Institution. Faraday was not much of a mathematician, but he had one of the greatest physical imaginations anyone has ever had, and he could picture what was going on in a way that nobody else could. Ørsted had shown that electricity could create magnetism. Faraday asked the obvious flip side of the question whether magnetism could create electricity, and in the year 1831, he proved that it could. He found that if you push a magnet through a coil of wire, you create a flow of electricity in the wire, but only while the magnet is moving. The motion is the key. A still magnet does nothing, but a moving one drives a current. This sounds like a small laboratory curiosity, and it is the single most important discovery for the world you actually live in. Every power plant on Earth, whether it runs on coal or gas or nuclear fuel or falling water or wind, does essentially the same thing at its heart. It spins magnets past coils of wire or coils past magnets to generate electricity, exactly as Faraday discovered. When you flip a light switch, you are reaching back across nearly 2 centuries to that bottle washer and his moving magnet. Faraday also came up with a way of picturing all this that changed physics forever. Instead of imagining that magnets and charges reach out and grab each other across empty space, he imagined that they fill the space around themselves with invisible lines of force, an unseen field that stretches out in every direction, and that other objects respond to the field around them. This idea of a field, a real physical thing that exists in empty space and carries force, was strange and new, and it would turn out to be one of the most important ideas in all of physics. Today we think the entire universe is made of fields. Before we get to what Maxwell did with all this, it is worth pausing on a question that had been splitting physicists down the middle for 200 years, because it matters enormously for the rest of the story. What is light, actually? Newton himself had an answer. He thought light was made of tiny particles, little corpuscles, streaming out from a source in straight lines. And given Newton's towering reputation, a great many people believed it simply because he had said so. But a Dutch contemporary of his named Christian Huygens disagreed, arguing that light was a wave, a spreading ripple, and for a century the two ideas sat side by side without a clear winner. The matter seemed to be settled, finally and decisively, right at the start of the 1800s by an Englishman named Thomas Young, who ran one of the most important and most beautiful experiments in the history of physics, and it is so simple you could almost do it at home. He shone light through two narrow, closely spaced slits and let it fall on a screen behind them. If light were a stream of particles, you would expect two bright lines on the screen, one behind each slit, like paint sprayed through two gaps. Instead, he saw a whole row of bright and dark stripes spread across the screen. The only way to explain those stripes is if light is a wave, because waves coming through the two slits overlap and interfere, so that where two crests meet, they add up into a bright band, and where a crest meets a trough, they cancel out into darkness, exactly the pattern you see when two sets of ripples cross on a pond. Young had shown that light interferes, which is something only waves do, and the particle idea was, for the moment, finished. Light was a wave. Remember how confident that conclusion was, because in 100 years, Einstein is going to walk in and show that the particle idea was not dead at all, and that light is somehow both, which is the kind of plot twist physics specializes in. There's also the question of how fast light travels, and the story of how we first measured that is worth a moment. Because for most of history, people assumed the speed of light was simply infinite, that light arrived everywhere the instant it left, with no travel time at all. Galileo had tried to measure it by standing on a distant hilltop from an assistant and uncovering lanterns to see how long the light took to cross between them. But light is far too fast for that to work, and all he could conclude was that it was very quick. The first real measurement came in the year 1676, and it came beautifully from watching the heavens. A Danish astronomer named Ole Rømer was carefully timing the moons of Jupiter, watching one of them disappear behind the giant planet over and over like clockwork. And he noticed something strange. The eclipses of that moon ran early when the Earth was closer to Jupiter and ran late when the Earth was farther away by several minutes. He realized the only sensible explanation was that light takes time to travel, and that when Earth is farther from Jupiter, the light simply has a longer distance to cross before it reaches us. So the eclipse looks delayed. From the size of that delay, he made the first real estimate of the speed of light, and although his number was a bit off, he had proven the enormous point that light has a speed at all, and that it is fast but not infinite. Later, more precise experiments on Earth by Frenchmen named Fizeau and Foucault, using spinning toothed wheels and rotating mirrors to time a flash of light over a known distance, pinned the number down to close to what we use today, about 186,000 miles every second. So by the time Maxwell came along, the speed of light was a famous, carefully measured number, which is exactly why what happened next was so shocking. But Faraday could not write his beautiful pictures down in the language of mathematics, and so the universe waited for someone who could, and that someone was a Scottish physicist named James Clerk Maxwell, who is probably the most important physicist most people have never heard of. In the 1860s, Maxwell took everything that was known about electricity and magnetism, all the discoveries of Volta and Ørsted and Ampere and Faraday, and he boiled it all down into a tidy set of equations, just a handful of lines of mathematics that together describe absolutely everything electricity and magnetism do. And then, while studying his own equations, he noticed something that stopped him cold. His equations said that a changing electric field creates a magnetic field, and that a changing magnetic field creates an electric field. So Maxwell realized you could have the two of them leapfrogging, each one creating the other over and over in a self-sustaining ripple that would travel outward through space on its own. He calculated how fast this ripple, this electromagnetic wave, would travel, working it out from numbers that had been measured in completely separate electrical experiments. And the speed that came out of his equations was about 186,000 miles every second. That number was already famous. It was the measured speed of light. Maxwell had not been studying light at all. He had been studying sparks and magnets and wires, and out of that work fell the exact speed of light, which could only mean one thing. Light itself is an electromagnetic wave. The light from the sun, the glow of a candle, the color of the sky, all of it is the same electricity and magnetism that Faraday had been playing with in his laboratory, rippling through space. Three great mysteries, electricity, magnetism, and light, had just collapsed into one, and the idea kept paying off. Maxwell's equations did not just explain the light we can see. They predicted that there should be electromagnetic waves of every possible wavelength, far beyond the narrow band our eyes happen to detect. A German physicist named Heinrich Hertz in the year 1887 set out to find them, and he succeeded, producing and detecting invisible waves in his laboratory that were exactly like light, but with wavelengths far too long for the eye to see. He had discovered what we now call radio waves, and although he reportedly saw no practical use for them, within a couple of decades they would carry voices across oceans. The whole modern world of radio, television, radar, microwave ovens, Wi-Fi, and the signal reaching your phone right now is built on the invisible waves that fell out of Maxwell's equations. Every one of those is the same stuff as visible light, just tuned to a wavelength your eyes cannot catch. There is one more 19th century triumph that deserves a mention here, because it did something that the greatest philosophers had flatly declared impossible, and it would later become one of the most important tools in all of science. Earlier in the century, when light was passed through a glass prism and spread into its rainbow of colors, a German lens maker named Joseph von Fraunhofer noticed that the sun's rainbow was not perfectly smooth. It was crossed by hundreds of thin, dark lines, gaps where particular colors were missing, and nobody knew why. Then, around the year 1860, two more Germans, the physicist Gustav Kirchhoff and the chemist Robert Bunsen, the man whose name is on the burner in every school chemistry lab, worked out what the lines meant. They found that when you heat any chemical element until it glows, and pass its light through a prism, it produces its own unique pattern of bright colored lines, a pattern as distinctive as a fingerprint, different for every element. And the dark lines in the sun's spectrum were the same patterns in reverse, the signatures of the elements in the sun's outer layers, absorbing exactly their own colors out of the sunlight passing through. This meant something staggering. By spreading out the light of a distant object and reading the lines, you could tell what it was made of without ever touching it or going there. A famous philosopher had declared, only a few decades earlier, that the chemical composition of the stars was a thing humanity could never, ever know, that it was forever beyond our reach. He was wrong almost immediately, because we can read the makeup of a star from nothing but its light, and in fact, the element helium was discovered in the sun by its lines before it was ever found on Earth, which is why it is named after the Greek word for the Sunday spectroscopy. This reading of the barcode in light is how we know what the universe is made of, and it is hiding inside that later mystery of why each atom glows with its own exact colors. The mystery Bohr was about to solve. So, by the year 1890 or so, physics was feeling extremely pleased with itself, and you can hardly blame it. Newton had explained motion and gravity. Thermodynamics had explained heat and energy. Maxwell had unified electricity, magnetism, and light. It really did look like the big questions had all been answered, and that what remained was just careful measurement, filling in a few more decimal places. There is a famous bit of physics legend that some senior figure declared around this time that physics was essentially finished, that there was nothing important left to discover, only more precise measuring to do. Whether anyone important truly said exactly that is doubtful, and historians are rightly skeptical of the quote, but it captures the mood of the era perfectly. The house of physics looked complete, and it was about to fall down because there were a few small problems left over, a couple of tiny clouds on an otherwise clear sky, and those tiny clouds were about to turn into the two greatest storms in the history of science. The first cloud had to do with light and with a question that sounds almost childish. If light is a wave, like Maxwell said, then what is it a wave in? Every other wave anyone knew of was a wave in something. Ocean waves are waves in water. Sound waves are waves in air. And a wave is just a wiggle passing through some material. So light, being a wave, ought to be a wiggle passing through some material too, and physicists gave that material a name, the ether, an invisible substance they assumed filled all of space, even the vacuum between the stars, so that light would have something to ripple through. The trouble was that nobody had ever detected this ether, so two American scientists, Albert Michelson and Edward Morley, designed an extraordinarily precise experiment to find it. Their reasoning was simple. The Earth is racing through space as it orbits the sun, so it must be moving through the ether like a boat moving through water, and that means there should be an ether wind blowing past us. Light traveling along with that wind should move at a slightly different speed than light traveling against it. The same way a swimmer is faster going downstream than up. So they measured the speed of light in different directions extremely carefully, expecting to see a difference. They found nothing. The speed of light was exactly the same in every direction, no matter how the earth was moving. It was as if the ether wind simply did not exist, or as if light somehow refused to be sped up or slowed down by our motion through space. This was deeply confusing, one of the most famous failed experiments in history, and it sat there unexplained, a small cloud that would not go away until a young patent clerk in Switzerland looked at it and decided that maybe the problem was not the experiment. Maybe the problem was our most basic assumptions about space and time themselves. That clerk was Albert Einstein, and the year everything changed was 1905, a year so productive for him that physicists simply call it his miracle year. He was 26 years old. He had not been able to find an academic job, and he was working in a patent office in Bern, doing physics in his spare time. In that single year, he published 4 papers, and any one of them would have made him famous. One of them explained the jittery, random dance of tiny particles suspended in water, which finally gave hard proof that atoms and molecules are real, settling a debate that had run since the ancient Greeks. Another explained a strange effect involving light knocking electrons out of metal, and we will come back to that one because it helped kick off the second great storm. A third laid out his theory of special relativity, and the fourth, a short follow-up to the third, contained the most famous equation in the history of the world. Special relativity starts from an idea so bold that it sounds almost reckless. Einstein simply accepted what the Michelson-Morley experiment was telling him, that the speed of light is always the same for everyone, no matter how they are moving. He took that as a rock-solid rule of the universe and asked what the consequences would have to be. And the consequences are staggering, because if the speed of light is truly the same for everyone, then space and time themselves cannot be the same for everyone. They have to bend and stretch to keep the speed of light fixed. Here is one way to feel why. Speed is just distance divided by time. If you and I are moving differently, but we both have to measure light at the exact same speed, then we cannot possibly agree on distances and times, because if we did, we would get different speeds for the light. Something has to give, and what gives is our old, comfortable, common sense belief that time ticks at the same rate everywhere, and that a meter is a meter for everyone. What Einstein showed is that the faster you move, the slower time passes for you, compared to someone standing still. Not slower as an illusion or a trick of the clocks, but genuinely slower. Moving clocks really do tick slow. Moving objects really do get shorter in the direction they are traveling. And two events that look like they happen at the same moment to one person can happen at clearly different moments to someone moving past, so that even the idea of now, of what is happening right this instant across the universe falls apart. None of this is noticeable in ordinary life because the effect only becomes large when you move at a serious fraction of the speed of light, and we crawl along far too slowly to feel it. But it is real, and we have measured it many times. Take two identical, extremely precise clocks, leave one on the ground, fly the other around the world in an airplane, and when they are brought back together, the one that flew has ticked a tiny bit less. The faster clock aged less. Time is not the universal, steady background we always assumed. It is part of the action, and it bends. The famous equation, the one you already know, is the simple summary of the fourth paper, and it says that energy equals mass times the speed of light squared. What it really means is that mass and energy are the same thing in different forms, that a tiny amount of mass is equal to an enormous amount of energy because the speed of light is such a huge number and you are squaring it. A paperclip's worth of matter, fully converted, holds enough energy to power a town. This is the principle behind the energy of the sun and behind nuclear power and, less happily, behind nuclear weapons, all of which work by turning a small amount of mass directly into a tremendous amount of energy. But in 1905, it was just a line of mathematics, a strange and beautiful consequence of taking the speed of light seriously. Einstein was not finished, though, because special relativity had a problem, and the problem was gravity. His new theory got along beautifully with everything except Newton's old picture of gravity, which assumed that gravity reached across space instantly. An instant was no longer allowed in a universe with a strict speed limit. So Einstein spent the next 10 years, the hardest decade of his working life, trying to fix it, and what came out in the year 1915 was general relativity, which is one of the most beautiful and surprising ideas any human being has ever had. It is his masterpiece. Newton had said that gravity is a force, an invisible pull reaching across space between any two masses. Einstein said no, gravity is not a force at all. Gravity is the bending of space and time. The idea is that space and time are woven together into a single flexible thing, which we call space-time, and that anything with mass, like a star or a planet, warps the space-time around it, the way a heavy ball resting on a stretched rubber sheet makes a dip. Other objects then move along the curves and dips of that warped space-time, and what we feel as the pull of gravity is really just things following the natural bends in space. The Earth does not orbit the sun because a rope of force is yanking on it, but because the sun has put the deep dip in space-time, and the Earth is rolling around the inside of that dip like a marble circling a bowl. The rubber sheet picture is not perfect, because the real bending happens in time as well as space and in more dimensions than a sheet can show, but it captures the heart of it. Matter tells space-time how to bend, and the bending of space-time tells matter how to move. This sounds like poetry, but it makes hard predictions that differ from Newton's, and that is what makes it science rather than just a lovely image. If gravity is really the bending of space, then even light, which has no mass, should be bent when it passes a heavy object because it is traveling through curved space. Einstein calculated exactly how much the sun should bend the light of distant stars passing near it. In the year 1919, during a total eclipse of the sun, when the moon blocked the sun's glare and made nearby stars visible in daytime, an expedition led by the British astronomer Arthur Eddington photographed those stars and measured their positions. The starlight had been bent by exactly the amount Einstein predicted. The news went around the world, and Einstein became, essentially overnight, the most famous scientist alive, the very picture of genius. His theory has kept passing every test we throw at it for over a century since. It predicted that time runs slower in stronger gravity, which sounds absurd, and yet your phone's location feature has to correct for exactly this, because the clocks on the satellites overhead, being farther from Earth's mass, tick faster than clocks on the ground, and without accounting for that, your maps would drift off by miles within a day. General relativity also predicted black holes, regions where space is bent so steeply that nothing, not even light, can climb back out. And it predicted ripples in space-time called gravitational waves, which we finally detected directly in the year 2015, a full century after Einstein wrote the theory down, from the collision of two black holes more than 1 billion years ago. So that was the first great storm, relativity, and it rebuilt our understanding of space, time, and gravity from the ground up. But the second storm was, if anything, even more disturbing because it did not just change the rules. It suggested that at the deepest level, the universe might not follow strict rules at all, only odds. This was the quantum revolution, and it grew out of that other small cloud, the one about light and heat. The cloud was this: when you heat something up, it glows, first dull red, then orange, then white hot, and physicists wanted to predict exactly what colors a hot object should give off at each temperature. It sounds simple, but when they used the trusted physics of the day to calculate it, the math gave an insane answer. It predicted that any warm object should be blasting out an infinite amount of energy at the blue and violet and ultraviolet end of the spectrum, which would mean that the warmth of your own body or a cup of tea should be flooding the room with deadly radiation. This obviously does not happen, or you would not be alive to watch this, and the absurd prediction got a suitably dramatic name: the ultraviolet catastrophe. The equations were broken, and nobody knew why. In the year 1900, a careful, conservative German physicist named Max Planck found a fix, and he found it almost by accident, and he hated it. He discovered that he could make the math come out right, matching the real glow of hot objects perfectly, but only if he made one bizarre assumption. He had to assume that energy does not flow smoothly in any amount you like, but only comes in tiny, discrete chunks, little indivisible packets, which he called quanta. It is the difference between a ramp and a staircase. The old physics assumed energy was a ramp where you could stop at any height. Planck found that the universe is built like a staircase, where you can only stand on the steps and never in between. Each packet of light energy he found was tied to its color, with bluer light carrying bigger packets and redder light carrying smaller ones, set by a tiny new number we now call Planck's constant, which is one of the smallest and most important numbers in all of science. Planck himself thought this was just a mathematical trick to make the equations work, not a real description of nature, and he spent years uncomfortable with it. But it was real, and it was the first crack of the second storm. It was Einstein again, in that same miracle year of 1905, who took the staircase seriously. In the paper that would later win him the Nobel Prize, he looked at a puzzle where shining light on certain metals knocks electrons loose, an effect that behaved very strangely. Brighter light did not give the electrons more energy, only more of them, while making the light bluer did give each electron more energy. This made no sense if light was simply a smooth wave. Einstein realized it made perfect sense if light came in packets, just as Planck's math had hinted, with each packet of blue light carrying a bigger punch than each packet of red. So light, which Maxwell had so triumphantly shown to be a wave, was now also, somehow, a stream of tiny particles, which we now call photons. And this is the heart of the madness that was coming, because light was clearly a wave, with experiments proving it stretched back 100 years. And now it was clearly also a particle, and both were true at once. A Danish physicist named Niels Bohr took the staircase idea and aimed it at the atom, and here it explained one of the oldest mysteries in chemistry. By this time, experiments had shown that an atom is mostly empty space, with a tiny, dense lump of positive charge at the center, the nucleus, and tiny negative electrons somewhere around it. The natural picture was a little solar system with electrons orbiting the nucleus like planets orbiting the Sunday. But that picture had a fatal flaw, because Maxwell's own equation said that an electron whirling in a circle should constantly bleed away energy as light and spiral into the nucleus in a tiny fraction of a second. Every atom in your body should have collapsed instantly. Bohr fixed this in the year 1913 with the staircase. He said, the electrons can only exist at certain specific distances from the nucleus, certain allowed steps, and never in between, so they cannot smoothly spiral inward. An electron can jump from a higher step to a lower one, and when it does, it spits out a single photon of light carrying exactly the energy of the gap it jumped, which is why each kind of atom glows with its own exact set of colors, a barcode of light that lets us tell from across the galaxy what the distant star is made of. But why should electrons only sit on certain steps? The answer, when it came, was the strangest idea yet. A French aristocrat named Louis de Broglie suggested in the year 1924 that if waves can act like particles the way light does, then maybe particles can act like waves. Maybe an electron is also somehow a wave, and the allowed steps in the atom are simply the orbits where the electron's wave fits neatly around the loop without canceling itself out, the way only certain notes fit on a guitar string of a given length. This sounded crazy, and then experiments confirmed it. Fire electrons at a barrier with two narrow slits, and they form the same striped wave pattern that water waves or light waves make, as if each single electron passes through both slits at once and ripples like a wave. Fire them one at a time, and each lands as a single dot, like a particle. But the dots, over thousands of runs, still build up the striped wave pattern. Everything is both, and which face it shows you depends on how you look. In the late 1920s, two physicists built this strangeness into a complete mathematical theory, working from different directions. A young German named Werner Heisenberg created one version using tables of numbers, and an Austrian named Erwin Schrödinger created another using a wave equation. And it turned out the two were secretly the same theory, wearing different clothes. This was quantum mechanics, and it works. It is, in terms of raw predictive accuracy, the most successful theory in the history of physics, agreeing with experiment to more decimal places than almost anything else we have ever measured. Every transistor in the device you are using, every laser, every LED, the entire chemistry of life, all of it runs on quantum mechanics. The theory is not in doubt. What is in doubt, even today, is what it actually means, because what it says about reality is genuinely hard to accept. Here is the part that broke Einstein's heart. Schrödinger's equation does not tell you where an electron is. It only tells you the odds of finding it in various places. The German physicist Max Born worked out that the wave is not a wave of any substance, but a wave of probability, a spread out fog of maybes. And the electron does not have a definite position at all until you actually look, at which point the fog of possibilities suddenly collapses to a single spot, seemingly at random. Before you measure it, the particle is genuinely not in any one place, but smeared across all its possibilities at once. Heisenberg then proved his famous uncertainty principle, which says there is a hard limit built into nature itself on how well you can know certain pairs of facts about a particle at the same time. The more precisely you pin down where a particle is, the more hopelessly uncertain its speed becomes, and the reverse. This is not a limit of our instruments that better tools could beat. It is a limit on what is knowable, because the particle itself does not possess both a sharp position and a sharp speed at once. Remember Laplace and his dream of a universe so perfectly clockwork that knowing everything about one moment would let you calculate the entire future? Quantum mechanics takes that dream and tears it up. At the deepest level we can reach, the universe does not seem to be a film already shot. It deals in probabilities, in genuine chance, in outcomes that are not decided until they happen. Einstein, who had helped start all this, could never accept it, and he spent the rest of his life arguing against it with his famous protest that God does not play dice with the universe. He kept inventing clever thought experiments to show that the theory must be incomplete, that there had to be some hidden, sensible reality underneath the randomness. And here is the remarkable thing. Those very arguments, especially one he made in the 1930s about two particles that stay mysteriously linked across any distance, a connection we now call entanglement, turned out to point at real effects. Decades later, experiments inspired by his objections were actually carried out, and they showed that Einstein was wrong and the strange quantum picture was right. The universe really is that strange. Two entangled particles really do stay linked, so that measuring one instantly tells you about the other, no matter how far apart they are, and there is no hidden clockwork underneath, restoring the old certainty. Einstein lost the argument, but the argument was so good that proving him wrong won a Nobel Prize in the year 2022, almost 90 years after he raised the point. All of this raises a question that physicists still argue about today, more than 90 years later, and it is not a question of mathematics, but of meaning. The equations of quantum mechanics work flawlessly, but they describe a particle, before you look at it, as a spread out cloud of possibilities in many places or many states at once. The moment you measure it, that cloud snaps to a single definite answer. So, what actually happens in that moment of looking, and why should the act of measuring change reality? Schrödinger, who wrote this central equation, was so bothered by this that he invented a famous thought experiment to show how absurd it seemed. He imagined a cat sealed in a box with a device that would release poison if a single radioactive atom happened to decay, an event governed by quantum chance. According to the strict math, until you open the box and look, the atom is in a blur of both decayed and not decayed, which would mean the cat is somehow both alive and dead at the same time, which is plainly ridiculous for a cat. He meant it as a criticism, a way of saying, surely something is missing here. And yet the puzzle he raised has never fully gone away. Physicists have come up with several ways of making peace with this, and they are called interpretations because they all use the exact same equations and make the exact same predictions, differing only in the story they tell about what is really going on. The oldest and most common, often called the Copenhagen interpretation after the city where Bohr worked, more or less says to stop asking, that the cloud of possibilities is simply the best description there is, and that it collapses to one answer when measured, and that wondering what the particle is doing when nobody looks is not a useful question. Another, far stranger idea, the many worlds interpretation, takes the math completely literally and says the cloud never really collapses at all, that instead the universe itself splits, so that in one branch the cat lives, and in another the cat dies, and both are equally real, just in separate worlds that can no longer touch, which would mean that every quantum event is constantly spawning countless parallel universes. There are other interpretations still, and the genuinely remarkable, slightly maddening thing is that we currently have no experiment that can tell these stories apart because they all predict precisely the same results in the laboratory. So we are in the unusual position of having a theory that works perfectly while honestly not knowing what it is telling us about reality, and reasonable physicists today still disagree about it. That is not a sign the theory is broken. It is a sign we have run into something genuinely deep about the world that we have not finished understanding. The quantum world had more surprises in it, and two of them are worth telling because they answer questions you have probably wondered about without knowing it. The first is this: if electrons in an atom can sit on different steps, different energy levels, then why do they not all just tumble down to the lowest step and pile up there together? An Austrian physicist named Wolfgang Pauli found the answer in the year 1925 in a rule now called the exclusion principle, which says that no two electrons can ever occupy the exact same state at the same time. They are forbidden by a deep law of nature from crowding into the same situation, so they are forced to stack up on higher and higher steps, filling the levels from the bottom up the way water fills a container from the bottom before it rises. This sounds like a tiny technical point, and it is the reason for the entire periodic table of the elements, because the way electrons are forced to stack into shells is what gives each element its character and its chemistry. And so the whole of chemistry, every reaction, every material, every living thing rests on this one stubborn rule that electrons will not share. It goes further than that. The exclusion principle is the real reason the floor holds you up, and the reason you cannot push your hand through a table. When you press on something solid, you are not feeling the atoms physically touching, because atoms are mostly empty space and never quite make contact. You are feeling the electrons in your hand refusing by this law to share space with the electrons in the table, pushing back against being crowded. The solidity of everything you have ever touched is, in the end, this quantum rule made large. The second surprise was a ghost. When physicists studied a certain kind of radioactivity where a nucleus spits out an electron, they found that some energy seemed to go missing in the process, as if the books simply would not balance. And this was alarming, because the conservation of energy was one of the most trusted laws in all of physics. In the year 1930, Pauli again, rather than give up the law, made a desperate proposal, suggesting that there must be another particle being emitted as well, one that carried off the missing energy while being almost impossible to detect, with no electric charge and almost no mass, slipping away unseen. He apologized for it, reportedly saying he had done a terrible thing by predicting a particle that could never be observed. It was named the neutrino, the little neutral one, a name coined by the physicist Enrico Fermi, and for over 20 years it remained purely hypothetical, a bookkeeping fix nobody could find. It was finally detected in the year 1956, and Pauli was proven right. Neutrinos turn out to be among the most common particles in the universe, with trillions of them streaming out of the sun and passing straight through the entire Earth and through your body every single second, almost never hitting anything because they barely interact with ordinary matter at all. As you watch this, an unimaginable flood of these ghostly particles is sailing through you and out the other side, and you feel absolutely nothing. Another twist in the quantum story predicted something nobody had ever imagined. In the year 1928, a quiet, famously precise English physicist named Paul Dirac set out to do something that sounds modest, which was to write a version of the quantum equations that also obeyed Einstein's relativity, so that the two great theories of the small and the fast would agree. When he succeeded, his equation had a strange feature he could not get rid of. It insisted that for every kind of particle, there should also exist a mirror image twin with the opposite electric charge, a sort of antiparticle. For the electron, this meant there should be a particle exactly like it, but with positive charge instead of negative. Dirac trusted his mathematics, even though no such thing had ever been seen. And in the year 1932, it was found a positive electron, now called the positron, appearing in the debris of cosmic rays from space, exactly as the equation had demanded. This was antimatter, and it was the first time anyone had predicted a whole new form of matter from pure mathematics and then gone and found it. When a particle of matter meets its antimatter twin, the two destroy each other completely and turn entirely into energy, the cleanest possible demonstration of Einstein's equation. This raises a genuine mystery that we still have not solved, because as far as we can tell, the Big Bang should have made matter and antimatter in equal amounts, which should have annihilated into nothing but light, leaving an empty universe. Instead, for reasons we do not fully understand, there was a tiny leftover of matter, about one extra particle for every billion pairs, and that tiny surplus is everything, every star, every planet, you. We are the rounding error in a vast cancellation, and nobody is quite sure why the books did not balance. Dirac's marriage of quantum theory and relativity grew into something even richer, a way of describing nature called quantum field theory, which is our deepest current language for the small. In this picture, the most basic things in the universe are not particles at all, but fields, invisible somethings that fill all of space, one for each kind of particle. And what we call a particle is just a little ripple, a concentrated vibration in its field. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field, and so on. This carries Faraday's old hunch about fields all the way to its conclusion, because in this view, the universe is, at bottom, a collection of fields, and matter is what happens when they vibrate. The first complete theory of this kind, finished in the late 1940s by several physicists, including the famously colorful American Richard Feynman, described how light and electrons interact, and it is the most accurately tested theory in all of science, matching experiment to about 1 part in a trillion, which is like measuring the distance across the country and being off by less than the width of a human hair. Feynman also gave physicists a wonderfully simple way to picture these interactions as little cartoons of lines meeting and parting, now called Feynman diagrams, which are scribbled on chalkboards in physics departments all over the world to this day. While all of this was unfolding, another group of physicists had been taking the atom apart to see what was inside it, and what they found rewrote our idea of matter itself, and, along the way, unleashed the most destructive force humanity has ever held. Remember Democritus and his uncuttable atom from 2,500 years ago. By the early 1900s, we had found the atom, and the very first thing we did was cut it. The first piece to come loose was discovered in the year 1897 by an Englishman named Joseph John Thomson, usually called J. J. Thomson, who was studying the eerie glow that appears when electricity is passed through a sealed glass tube with the air sucked out, a beam that came to be called a cathode ray. He showed that this beam was made of tiny particles, far smaller and far lighter than any atom, carrying negative charge, and that they seemed to come out of the atoms of whatever metal he used, which meant the atom was not the smallest thing after all. He had discovered the electron, the first piece of an atom ever found, and with it came the realization that the supposedly uncuttable atom had parts inside it. At almost the same moment, nature handed physicists a second clue that the atom had a hidden inner life, and this one was discovered entirely by accident. In the year 1896, a French scientist named Henri Becquerel left some uranium salts sitting on top of a wrapped, unexposed photographic plate in a drawer, expecting nothing, and when he developed the plate later, he found it fogged, as if it had been exposed to light, even though it had sat in total darkness. The uranium was giving off some kind of invisible ray, all on its own, with no outside power source, drawing on energy that seemed to come from nowhere. This was radioactivity, and it was deeply mysterious because it appeared to break the sacred law that energy cannot come from nothing. A young researcher named Marie Curie, working in Paris with her husband Pierre, took up the puzzle and gave the phenomenon its name. She discovered that the rays were coming from inside the atoms themselves, from the heart of the atom slowly breaking apart, and in the course of this work she found two entirely new elements, one of which she named polonium after her homeland of Poland, and the other radium. Marie Curie would go on to become the first person ever to win 2 Nobel Prizes, and she remains the only person ever to win the prize in 2 different sciences. And she did it as a woman in a field that had almost no room for women, while the radioactive materials she handled with her bare hands slowly poisoned her, eventually killing her. Her notebooks remain so radioactive more than a century later that they are kept in lead-lined boxes and must be handled with protective gear. Radioactivity was the first hint that there was a tremendous store of energy locked inside the nucleus of the atom, the same energy that would later light cities and level them. So, as the new century opened, physicists knew the atom had at least one part, the negatively charged electron, and they knew that atoms could break apart and release energy from somewhere deep inside. The picture of the atom at that point was a vague one, a kind of soft, positive blob with the negative electrons stuck in it like raisins in a pudding. And it was this pudding picture that Ernest Rutherford was about to destroy. A New Zealand born physicist working in England, Rutherford fired tiny positive particles at an incredibly thin sheet of gold foil, expecting them to sail straight through, since the atom was thought to be a soft, evenly spread blob. Most of them did pass through, but every so often, one bounced almost straight back, which stunned him. He said it was as surprising as firing a large shell at a sheet of tissue paper and having it come back and hit you. The only way to explain it was that nearly all of an atom's mass and all of its positive charge is crammed into a fantastically tiny, dense core at the center, the nucleus, with the electrons way out at the edges and almost the entire atom being empty space. If an atom were the size of a sports stadium, the nucleus would be about the size of a pea at the center, and everything else would be empty. The solid floor under your feet is, on the inside, almost entirely nothing. The nucleus turned out to contain positively charged particles called protons, and later, in the year 1932, an Englishman named James Chadwick discovered a second kind of particle in there with no charge at all, the neutron. And this is where mass and energy, the two things Einstein had shown were really one, came together in the most consequential way. Physicists found that the nucleus of a heavy atom could be split apart, a process called fission, and that the pieces left over weighed very slightly less than the original. That missing mass had not vanished. It had turned into energy, exactly as the famous equation said it would. And because you are multiplying by the speed of light squared, even a microscopic amount of missing mass becomes a colossal amount of energy. In the 1940s, during the Second World War, this knowledge was turned into the atomic bomb, and physics, which had spent its whole history simply trying to understand the world, suddenly had the power to end cities. The same understanding also gave us nuclear power plants, and it explained, finally, what makes the sun shine, because the sun runs on the opposite process, fusion, squeezing light atoms together so hard that they merge into heavier ones and release energy, again, from a tiny loss of mass. Every bit of sunlight that has ever warmed your face is mass from the heart of the sun that has been turned into light. Now, you might think that once we had the proton, the neutron, and the electron, we had reached the bottom, the truly uncuttable pieces. At last, we had not. When physicists built machines to smash particles together at enormous speeds, called particle accelerators, they found a bewildering crowd of new particles tumbling out of the collisions, dozens and dozens of them. so many, that one frustrated physicist compared it to a zoo, and another said that if he had known there would be this many, he would have become a botanist. It was a mess, and a mess in physics is usually a sign that there is a simpler picture hiding underneath. Just as the tangled circles of the old Earth centered astronomy had been hiding a simpler sun centered truth, the simpler picture arrived in the 1960s when a physicist named Murray Gell-Mann, among others, proposed that the proton and the neutron and most of the particle zoo were not basic at all, but were each built from even smaller things, which he gave the playful name quarks. The proton and neutron are each made of three quarks stuck together. So Democritus was wrong twice over. The atom could be cut into a nucleus and electrons, and the nucleus could be cut into protons and neutrons, and the protons and neutrons could be cut into quarks. As far as we can tell today, the quarks and the electron really are the bottom, with no smaller pieces inside. But then, people have thought they reached the bottom before. Out of all this came what is today our best and most complete theory of what the world is made of and how its pieces interact with the rather plain name of the Standard Model of particle physics. It took the second half of the 20th century to build by many hands, and it is one of the crowning achievements of the human mind, even if almost nobody outside physics has heard of it. It says that all the ordinary matter in the universe is built from just a small handful of basic particles, a few kinds of quarks, and a few kinds of particles, like the electron, and that these particles push and pull on each other through a small number of forces, each force carried by its own particle that the others toss back and forth between them, a bit like two skaters throwing a ball back and forth and being pushed apart by it. The light and electricity force is carried by the photon. There is a force that holds the quarks together inside protons, and a force responsible for certain kinds of radioactivity. The Standard Model ties three of nature's four known forces into a single framework and has predicted the results of experiments with breathtaking accuracy again and again. It is worth slowing down on those forces, because reducing all the pushing and pulling in the universe to just four basic kinds is one of the quiet triumphs of physics. The first is gravity, the weakest of them all by an almost absurd margin, and yet the one that shapes the whole universe at large scales, because it never cancels out and reaches across any distance. The second is the electromagnetic force, the one Maxwell unified, responsible for light, electricity, magnetism, chemistry, and essentially every force you feel in daily life that is not gravity. Because when you push a door or feel the ground, you are feeling electromagnetism between atoms. The third and fourth are forces that only act inside the nucleus, across distances far smaller than an atom, which is why nobody noticed them until the 20th century. The strong force is the strongest of the four, and it is the glue that binds quarks together into protons and neutrons, and binds those together into the nucleus, and it has a bizarre feature that, unlike every other force, it gets stronger as you try to pull the quarks apart, like a stretching rubber band, which is why you can never isolate a single quark on its own, no matter how hard you pull. The fourth is the weak force, which is responsible for certain kinds of radioactive decay, and which, despite its modest name, plays a starring role, because it is the weak force that lets the sun burn at all. allowing one kind of particle to slowly turn into another in the reactions that power every star. And here physics has been chasing a dream that goes all the way back to that first idea on the Turkish coast, the dream that the many are secretly one. Just as electricity and magnetism turned out to be two faces of a single force, physicists in the 1960s and 70s, including Sheldon Glashow, Abdus Salam, and Steven Weinberg, show that the electromagnetic force and the weak nuclear force are themselves two faces of a single deeper force, which they called the electro-weak force, that splits into the two we see only because the universe has cooled down so much since the Big Bang. At the searing temperatures of the very early universe, those two forces were one. This unification was confirmed when the particles it predicted were discovered, and it won a Nobel Prize. The hope is that the strong force, and one day even gravity, might join the same family, all of them turning out to be different low temperature faces of one original force that ruled the first instant of creation. We have not gotten there. Gravity, in particular, stubbornly refuses to join, for reasons we will come to. But the pattern, the steady collapsing of many things into fewer, is the same pattern that has driven physics since Thales guessed at his water, and it is still pulling us forward. The last great piece of it, to be confirmed, answers a question that sounds almost too basic to ask, which is why anything has mass at all. The theory predicted that all of space is filled with an invisible field, now called the Higgs field, and that particles get their mass from how strongly they drag through this field as they move, the way a person wading through deep water moves more heavily than someone walking through air. Particles that interact strongly with the field are heavy. Particles that barely notice it are light, and the photon which ignores it completely has no mass, and so flies at the maximum speed. This field was predicted in the year 1964 by Peter Higgs and several others working separately, and for nearly 50 years it remained just a prediction, because to confirm a field you have to stir it up and knock loose its particle, the Higgs boson, and doing that required the largest and most complex machine humanity has ever built. That machine is the Large Hadron Collider, a ring 17 miles around, buried underground near Geneva, where protons are whipped to nearly the speed of light and smashed together. In the year 2012, the teams there announced that they had found the Higgs boson, exactly as predicted, completing the Standard Model after almost half a century of searching. Peter Higgs, by then an old man, was in the audience and was seen wiping away tears. It would be easy to think that 20th century physics was all about the very large and the very small, about cosmic eclipses and giant colliders. But there was a third revolution going on at the same time, much quieter and far closer to home, and it is the one that actually built the world you live in. It is the physics of ordinary stuff, of solids and metals and crystals, the branch usually called condensed matter physics, and it took quantum mechanics and asked a humble question, which is what happens when you have not one or two particles, but trillions upon trillions of them packed together into a chunk of material. The answers turned out to run the modern world. By understanding through quantum mechanics exactly how electrons move through certain crystals, physicists came to understand a class of materials called semiconductors, which sit halfway between conductors that carry electricity freely and insulators that block it, and whose flow of electricity can be switched on and off and controlled. In the year 1947, at a research laboratory in the United States, three physicists built the first transistor out of such a material, a tiny switch with no moving parts that could turn a current on or off or amplify it. That single invention, born straight out of quantum theory, is the seed of every computer, every phone, every digital device that exists, and we now pack billions of transistors onto a chip smaller than a fingernail. The screen you are watching this on is a direct descendant of physicists trying to understand how electrons behave inside a crystal. The same deep understanding gave us the laser, which works by coaxing a huge number of atoms to all release their light in perfect step, producing a beam so orderly and pure that it can read the tiny pits on a disk, carry the entire internet as pulses of light through glass fibers thinner than a hair, and perform surgery on the eye. It also revealed some of the strangest behavior in all of physics, like superconductivity, where certain materials, cooled to extreme cold, suddenly lose all resistance to electricity and let a current flow around a loop forever without fading, and superfluids, liquids so cold and so quantum that they flow with no friction at all and will, eerily, creep up the walls of their container and escape on their own. These are not laboratory curiosities only. The same superconducting magnets are what bend the proton beams in that giant collider near Geneva and what create the magnetic fields in the scanners that let doctors see inside your body without cutting you open. Quantum mechanics, the theory nobody could quite believe, turned out to be the most practical theory ever written, hiding inside nearly every machine you touch. While these physicists were looking at ordinary matter, and others were looking inward at the smallest things, another group had turned Einstein's general relativity outward to the largest thing of all, the entire universe. And what they found there is just as strange. When Einstein first applied his equations to the whole cosmos, they told him the universe should be either expanding or contracting, never sitting still, and he found this so hard to believe that he added an extra term to his equations just to hold the universe steady, a fudge he later called the biggest blunder of his life, because in the year 1929, an American astronomer named Edwin Hubble, using the largest telescope in the world at the time, looked out at distant galaxies and discovered that they are nearly all racing away from us, and that the farther away a galaxy is, the faster it is fleeing. The universe was not steady at all. It was expanding, exactly as the unfudged equations had said, with every galaxy rushing apart, from every other like dots painted on the surface of a balloon that is being blown up. And if the universe is expanding now, then running the film backward means that long ago everything was closer together, and further back still, everything must have been crammed into an unimaginably hot, dense state, and then begun expanding from there. This is the Big Bang, the idea that the entire universe, all of space itself, began about 13.8 billion years ago in an incredibly hot, dense beginning and has been expanding and cooling ever since. It is worth clearing up the most common misunderstanding right away. The Big Bang was not an explosion that went off at some particular spot in empty space, scattering matter outward. It was the expansion of space itself, happening everywhere at once. And there was no outside and no center, because space did not exist beforehand to have a center in. The galaxies are not flying apart through space so much as the space between them is stretching. This sounds like a wild story, and the reason we believe it is that it made a prediction that came true in spectacular fashion. If the universe really began hot and dense, then there should be a faint afterglow of that early heat still soaking the whole sky, stretched out by billions of years of expansion into a cold, dim radio hiss coming from every direction at once. In the year 1965, two scientists at a telephone company laboratory, Arno Penzias and Robert Wilson, were trying to get rid of an annoying hiss in their radio antenna, a hiss they could not eliminate no matter what they did. Even after cleaning out the pigeon droppings they suspected were the cause, it turned out they were not picking up a fault in their equipment. They were picking up the leftover glow of the Big Bang itself, the oldest light in the universe, released when the cosmos was only a few 100,000 years old. They had stumbled onto the strongest evidence we have for how everything began, and they had nearly cleaned it away as noise. That afterglow, the cosmic microwave background, is still arriving at the Earth from all directions every second, and a tiny fraction of the static you might once have seen on an old untuned television set was that ancient light. It is worth giving credit for the Big Bang idea to the man who really had it first, because he was an unlikely figure, a Belgian Catholic priest and physicist named Georges Lemaitre. Years before the afterglow was found, and even before Hubble published his measurements, Lemaitre worked through Einstein's own equations and concluded that the universe must be expanding, and that if you ran it backward, it must have begun from a single concentrated starting point, which he called the primeval atom. Einstein himself initially dismissed it, reportedly telling Lemaitre that his calculations were correct, but his physics was abominable, because Einstein was still clinging to the idea of a steady, unchanging universe. Einstein later came around and admitted he had been wrong. It is a nice detail of history that the man often credited with the original Big Bang idea wore a priest's collar, and that he was careful to insist his science said nothing one way or the other about questions of faith, treating them as separate matters entirely. The Big Bang picture also lets us tell, with real confidence, the story of the first few minutes of everything, and the story is remarkable. In the very early universe, everything was so hot that atoms could not exist, because any atom would instantly be blasted apart. so there was only a roiling soup of the most basic particles. As the universe expanded and cooled, in the first few minutes, the lightest nuclei could form, and physicists can calculate exactly how much of each should have been made in that brief window, mostly hydrogen and helium in a very specific ratio, with a tiny trace of a few others. When we look out at the oldest, most untouched gas in the universe, we find exactly those proportions, which is one of the strongest confirmations that the hot early universe was real. Every hydrogen atom in every drop of water in your body was forged in those first few minutes after the beginning, almost 14 billion years ago, and has been around essentially ever since. The heavier elements, the carbon and oxygen and iron that make up you and the Earth, came much later, cooked inside stars, and scattered when those stars died, which is the source of the often repeated and entirely true idea that we are made of stardust. There is one more piece, and it is among the strangest. When physicists looked closely at the early universe, they found a puzzle. The afterglow of the Big Bang is almost perfectly smooth and the same temperature in every direction, even in regions on opposite sides of the sky that, by the ordinary story, should never have been able to touch or share heat because there was not enough time since the beginning for any signal to cross between them. So, how did they end up so identical? In the year 1980, a physicist named Alan Guth proposed a bold answer called inflation. The idea that in the tiniest fraction of the first second, far less than a trillionth of a second, the universe went through a burst of unimaginably fast expansion, ballooning in size by an enormous factor almost instantly. If that happened, then the whole visible universe grew out of a tiny patch that had been in contact and evened itself out before being stretched apart, which would explain the smoothness. Inflation is widely accepted because it explains several puzzles at once and has passed some real tests, but it is honest to say we do not know for certain that it happened or what could have driven it, and it remains an area of active argument at the frontier. So by the early 21st century, physics had two magnificent theories that together explained almost everything we could see. General relativity handled the very large gravity, stars, galaxies, the shape and history of the whole universe. Quantum mechanics handled the very small atoms, particles, light, the inner workings of matter. Between them, they cover an astonishing range, and both have passed every test we have devised. You would think this would be a happy ending, a finished house at last. It is not, and the reason is one of the deepest open problems in all of science, the thing physicists are still wrestling with right now. The two great theories do not get along. They flatly contradict each other. General relativity describes a smooth, curved, continuous space-time, while quantum mechanics describes a jittery world of discrete packets and probabilities. And when you try to force them together, when you try to ask what gravity does at the scale of a single particle, the mathematics falls apart and spits out nonsense, infinities where there should be answers. Or most situations, this does not matter because gravity is far too weak to notice at the scale of particles, and quantum effects are far too small to notice at the scale of stars. So the two theories rarely have to be in the same room, but there are places where the very small and the very heavy meet, and there both theories are needed at once, and there our understanding simply breaks down. The center of a black hole is one such place. The very first instant of the Big Bang is another. At those points, our two best descriptions of reality both demand to be used, and both refuse to work together, which is a flashing sign that something deeper is missing, some grander theory that would contain them both, a theory of quantum gravity that we do not yet have. The leading attempt, called string theory, suggests that the basic particles are not points at all, but unimaginably tiny vibrating strings, with different vibrations giving different particles, the way one guitar string can play many notes. It is a beautiful idea, but after decades of work, it has not yet made a prediction we can actually test. So it remains, for now, a hope rather than an answer. And honestly, nobody knows how this chapter ends. And it gets humbler than that, because in the last few decades, we have discovered that we do not even know what most of the universe is made of. When astronomers measure how galaxies spin, they find that the stars at the edges are moving far too fast, so fast that the galaxies should be flying apart, and the only way they hold together is if there is some enormous amount of extra, invisible mass we cannot see, tugging with its gravity. We call it dark matter, and there appears to be roughly 5 times as much of it as all the ordinary matter, all the stars and planets and gas and people put together. We have no idea what it is. It is not made of atoms. It gives off no light, and despite great effort, we have never directly caught a particle of it. And then, in the late 1990s, it got stranger still, because astronomers measuring the expansion of the universe expected to find it slowing down under the pull of all that gravity, and instead, they found that the expansion is speeding up as if some unknown pressure is pushing the universe apart faster and faster. They named the cause dark energy, and it appears to make up the majority of everything there is, around 2/3 of the whole universe. We have no idea what that is either. So, if you add it up, the ordinary matter that makes up you and the earth and every star you can see is only about 5% of the universe. The other 95%, the dark matter and the dark energy, is stuff we have detected only by its effects and otherwise do not understand at all. After 400 years of triumphs, physics has arrived at a strange and humbling place, having figured out the rules governing almost everything we can see, only to discover that what we can see is the small part. There is one more idea from the early 20th century that deserves a place in any honest history of physics, even though it is almost unknown outside the field, because it is one of the deepest and most beautiful truths we have ever found, and it came from a mathematician who was shut out of the academic world for the crime of being a woman. Her name was Emmy Noether, and the theorem she proved around the year 1918 calmly reorganized the whole of physics around a single profound principle. What Noether showed is that there is a deep and exact connection between symmetry and the conservation laws that physicists hold most sacred, the rules that say certain quantities, like energy and momentum, can never be created or destroyed. Before her, these conservation laws were treated as separate facts about the world, observed to be true, but not really explained. Noether revealed that they are not separate facts at all, but consequences of the symmetries of nature, and that insight runs through everything physicists have done since. To get a feel for what this means, you have to understand what a symmetry is in this sense, which is simply something that stays the same when you change something else. The laws of physics, for example, are the same today as they were yesterday and will be tomorrow. That is a symmetry, a sameness across time. The fact that the rules do not change from one moment to the next. The laws are also the same here as they are anywhere else in space, and the same whichever direction you happen to be facing. These sound like obvious, almost trivial observations, hardly worth stating, but Noether proved something staggering about them. She showed that the fact that the laws of physics do not change over time is the very reason that energy is conserved, that the two are mathematically, inescapably linked. The conservation of energy, that bedrock principle, is a direct consequence of the symmetry of time, and it goes further, with each symmetry giving rise to its own conservation law in a precise pairing. Because the laws of physics are the same everywhere in space, momentum is conserved. Because they are the same in every direction, the quantity called angular momentum, the thing that keeps a spinning top spinning and a planet orbiting, is conserved symmetry by symmetry. Noether's theorem ties the deep regularities of the universe to the quantities that never change, revealing that conservation laws are not arbitrary rules the universe happens to follow, but the unavoidable shadow of its symmetries. This is the kind of insight that, once you grasp it, changes how you see all of physics, because it means that the constancy of the laws of nature and the conservation of the great quantities are two faces of the same thing. Modern physics, especially the search for the deepest laws of particles and forces, is now conducted almost entirely in this language of symmetry, hunting for the symmetries of nature and the conservation laws they imply. What makes Noether's story more remarkable and more troubling is how hard the world made it for her to do this work at all. She was a brilliant mathematician in Germany at a time when women were largely barred from holding real university positions. And when she came to the famous university at Göttingen, some of the faculty objected to letting a woman teach, reportedly asking what the soldiers returning from war would think to find themselves learning at the feet of a woman. For years, she was allowed to lecture only under a male colleague's name and worked without a proper salary or title, doing world-class mathematics on the margins of an institution that would not fully admit her. The great mathematician David Hilbert, who fought to keep her there, is supposed to have responded to the objections by pointing out that the university was a place of learning, not a bathhouse, and that he saw no reason a candidate's sex should be an argument against her. Despite all of this, Noether produced some of the most important mathematics of the century. Her story took a darker turn when the Nazis came to power, because Noether was Jewish, and like Einstein and so many others, she was forced out of Germany, fleeing to the United States, where she taught at a women's college for a short time before dying suddenly at only 53 from complications after surgery. Einstein, who deeply admired her, wrote after her death that she was the most significant creative mathematical genius produced since the higher education of women began. A generous tribute to a colleague the world had treated shabbily. Today, Noether's theorem is regarded as one of the most profound results in all of physics, taught to every serious student of the subject, and her name, once kept off her own lectures, is now spoken with reverence. It is a reminder, like the stories of Marie Curie and Cecilia Payne and others we have met, of how much brilliance the field nearly lost, and in some cases did lose, to prejudice, and of how the deepest truths of nature do not care in the slightest about the sex or background of the mind that finds them. Remember Laplace and his grand dream of a universe so perfectly clockwork that an intelligence knowing the position and motion of every particle could calculate the entire future with certainty. We saw how quantum mechanics shattered that dream by introducing genuine chance at the deepest level. But there is another, separate way that the clockwork dream falls apart, and it is one that does not require quantum mechanics at all, that lurks even within Newton's own perfectly deterministic physics, and it was not really appreciated until the second half of the 20th century. It is called chaos, and it reveals that even in a completely deterministic universe, where the future really is fixed by the present, that future can still be utterly unpredictable in practice. The discovery came, fittingly, from someone trying to predict the weather. In the early 1960s, a meteorologist named Edward Lorenz was running a simple computer model of the atmosphere, and one day, to save time, he restarted a calculation partway through by typing in the numbers from an earlier printout, rounding them off very slightly, just a tiny difference far out in the decimal places. The kind of rounding anyone would assume could not possibly matter. But when he came back, the weather his model predicted had diverged completely from the original run, bearing no resemblance to it at all. That minuscule rounding, a difference too small to seem to matter, had grown and grown until it changed everything. Lorenz had stumbled onto one of the most important ideas in modern science, that some systems are so exquisitely sensitive to their starting conditions that the tiniest difference in where they begin leads to wildly different outcomes down the line. This sensitivity became famous under a memorable name, the butterfly effect, from the idea that something as small as the flap of a butterfly's wings, by stirring the air ever so slightly, could in principle set off a chain of events that determines whether a tornado forms weeks later on the other side of the world. The butterfly does not power the tornado, of course, but the tiny disturbance it makes can grow, through the chaotic dynamics of the atmosphere until it tips the balance toward one outcome rather than another. This is the heart of chaos, that in certain systems, small causes can have enormous, unpredictable effects, with tiny differences amplifying exponentially over time until all predictability is lost. And the weather is exactly such a system, which is precisely why, no matter how good our instruments and computers become, we will never be able to forecast the weather accurately more than a couple of weeks ahead, because the tiny gaps in our knowledge of the present always blow up into total uncertainty about the distant future. What makes chaos so philosophically profound is that it has nothing to do with randomness. A chaotic system can be completely deterministic, following Newton's laws exactly, with no chance involved at all, and yet still be impossible to predict, because to predict it, you would need to know its starting conditions with perfect, infinite precision, which is impossible. The future is, in principle, fixed by the present in these systems, just as Laplace dreamed, and yet it is unknowable, because any error in measuring the present, however small, ruins the prediction. So Laplace's demon, that imagined intelligence that could calculate the whole future, would fail even in a purely classical deterministic universe, not because the future is undetermined, but because knowing the present perfectly enough to compute it is impossible. Determinism, it turns out, does not guarantee predictability, and that distinction, drawn so sharply by chaos theory, is one of the deepest lessons of 20th century physics. Chaos is not some rare curiosity either, but is woven all through nature, in the turbulent flow of fluids, the dripping of a faucet, the rhythms of the heart, the dynamics of populations, the long-term motion of the planets, and the swirling of the atmosphere. For a long time, scientists had long assumed that simple rules led to simple, predictable behavior, and that the messy unpredictability of the world came from its complexity. Chaos theory revealed the opposite, that even the simplest deterministic rules can produce behavior of endless, unpredictable richness, and that, hidden inside the apparent randomness of chaotic systems, there are often beautiful, intricate patterns, a strange order woven through the disorder. It was a humbling discovery, showing that the universe is far less predictable than the triumphant clockwork picture of the 18th and 19th centuries had promised, not only because of quantum chance at the smallest scale, but because of chaos at every scale, an unpredictability built into the very heart of deterministic physics itself. It is worth pausing on a few of the experiments that turned the strange ideas of quantum physics from clever theories into hard, confirmed facts, because the theory we have been describing did not win out by elegance alone, but by surviving test after test. One of the most important came in the year 1923, when an American physicist named Arthur Compton fired X-rays at electrons and found that the X-rays bounced off and came away with less energy, having transferred some of their punch to the electrons, exactly as if the light were made of particles colliding like billiard balls. This was a direct, undeniable demonstration that light carries momentum and behaves as particles, just as Einstein had argued with his photons, and it convinced many of the remaining doubters. After Compton, it was very hard to deny that light, that supposed wave, really did come in particle-like packets that could knock electrons around. Around the same time, another experiment revealed a property of particles so strange it had no equivalent in the everyday world at all. When physicists sent a beam of atoms through a carefully shaped magnetic field, expecting the beam to spread out smoothly, they found instead that it split cleanly into two separate beams, as if each atom were forced to choose between just two possible orientations, with nothing in between. This pointed to a new quantum property, eventually called spin, a kind of intrinsic angular momentum that particles carry, but one that can only take certain discrete values, snapping to one of a fixed set of options rather than pointing any which way. Spin is genuinely impossible to picture in ordinary terms, since the particle is not really a tiny spinning ball, and yet it is real, measurable, and crucial, underlying everything from the structure of atoms to the magnets on your refrigerator to the scans that let doctors see inside your body. Quantum mechanics kept turning up features of reality that simply have no counterpart in the world our intuition was built for. The quantum theory has gone on to become the most precisely tested theory in the history of science, agreeing with experiment to a degree that is almost hard to believe. The theory predicts a certain property of the electron related to its magnetism, and when physicists calculate that property using quantum theory and then measure it in the laboratory, the calculation and the measurement agree to about 12 decimal places, an accuracy so extraordinary it is like measuring the distance from New York to Los Angeles and being off by less than the width of a human hair. No other theory in any science has ever been confirmed to such breathtaking precision. This is why, for all its strangeness, physicists trust quantum mechanics so completely, because every time they push it to the most extreme test they can devise, it passes, matching reality more closely than anything else we have ever measured. And yet, even this triumphant theory shows hints that it is not the final word, that there is physics beyond what we currently understand, and one of the clearest cracks came from the ghostliest particle of all, the neutrino. Recall that the neutrino was the nearly undetectable particle predicted to save the conservation of energy, the one that streams through your body by the trillions every second. For decades, the Standard Model assumed neutrinos had no mass at all, that they were perfectly weightless. But around the turn of the millennium, careful experiments revealed something unexpected, that neutrinos actually change from one type into another as they travel, a behavior called oscillation that is only possible if neutrinos have at least a tiny bit of mass after all. This was a genuine surprise and an important one, because it meant the standard model, that crowning achievement we celebrated earlier, was incomplete, that it had gotten something wrong, that there was new physics it could not account for. The discovery earned a Nobel Prize and stands as one of the few solid, confirmed hints we have of physics lying beyond our best current theory. These cracks matter because they are the threads that the next generation of physicists will pull on, hoping to unravel a deeper theory. There are others too, small disagreements between theory and experiment in a handful of ultra precise measurements, tantalizing hints that the standard model may be hiding something, though it is still unclear whether these are real cracks or will melt away with better measurements, and physicists are watching them closely. This is how progress in physics has always worked, not just through grand triumphs, but through the careful noticing of small things that do not quite fit, the tiny discrepancies that, often enough, turn out to be the first sign of a whole new world waiting to be discovered, just as the small clouds over 19th century physics turned into relativity and the quantum. The story is not finished, and the small puzzles of today may well be the revolutions of tomorrow. So look back at the whole road for a moment. It started with a man on the coast of Turkey guessing that everything was secretly made of one simple substance, and he was wrong about the water but right about the dream. It ran through Aristotle being confidently mistaken for 2,000 years, through Galileo rolling balls down a ramp and patiently proving the great man wrong, through Newton tying the falling apple to the orbiting moon with a single equation, through Faraday's moving magnet and Maxwell's startled realization that light is electricity rippling through space. It ran through Einstein bending time and space and gravity, through Planck's reluctant staircase, and the whole probabilistic strangeness of the quantum world, through the splitting of the atom and the building of the standard model, all the way out to an expanding universe born in a hot, dense beginning, and now flying apart faster and faster for reasons we cannot name. And the same dream Thales had, that the messy variety of the world comes down to something simpler underneath, is still the dream pulling physics forward. Right now, we are still looking for the water. What I find worth sitting with is that the story is so obviously unfinished. We have two magnificent theories that refuse to agree with each other. We have detected 95% of the universe only by the way it tugs on the small part we understand, and we genuinely do not know what that vast majority is. We do not know why there is something rather than nothing left over from the Big Bang, or what happens at the center of a black hole, or whether time has a true beginning. Every generation of physicists has felt at some point that the house was nearly complete, that only a little decorating remained, and every generation has turned out to be standing in a doorway with whole new wings of the building stretching off into the dark beyond it. The people who said physics was finished in the 1890s. We're standing right at the edge of relativity and the quantum, the two biggest discoveries that were still to come. And maybe that is the remarkable thing about all of this. Every single one of these rules was here the whole time, running everything, while nobody had any idea. The coffee was always cooling for the same reason the universe has a direction in time. The floor was always holding you up because of electrons refusing to share their space, even though the atoms in your feet never truly touch it. The light from the sun was always 8 minutes old by the time it warmed your face. None of it waited for us to understand it. We simply lived inside the rules, like that fish in the water, and then, slowly, over a few hundred years, with ramps and prisms and magnets and telescopes and the largest machines we have ever built, we started to see the water. And the most honest thing physics can tell you today, after everything, is that we have only just begun to look.